Hello everyone, welcome back to my YouTube channel. So as you know that I have started one lecture series called Linear Algebra for engineering students. So I have already uploaded 3 lecture videos in this lecture series. So today we'll understand one of the most beautiful ideas in a linear algebra, which is called eigenvalues and eigenvectors. So these eigenvalues and eigenvectors are not just mathematics. They power Google search, artificial intelligence, vibration analysis, and quantum physics. If you imagine stretching a vector without changing its direction, so that is where the eigenvectors concept born, right? So after a transformation, also some directions remain unchanged. So this is why unchanged. This answer lies in eigenvectors. So uh, if linear algebra have had a superstar concept like that, so these eigenvalues and eigenvector would be the definitely on the list. So let's decode eigenvalues and eigenvectors in the simplest possible way. So before going to discuss the eigenvalue and eigenvectors, we should know one concept which is called characteristics equation of a matrix. So if you discuss the characteristics equation of a matrix, so suppose you have a matrix n by n, that means n number of columns, n number of rows you have, then the characteristics polynomial is called the determinant of a minus lambda I. Okay, so lambda is a scalar. So if we take this A, the matrix is this one, A11, A12, A1n. Then next A21, A22, A2n. Then here more rows are there. The last row I am saying n1, n2, nn. Then if we take this A and A minus lambda I, you know I is the identity matrix. If A is the n order matrix, then I also you have to take order n. So this is representing A minus lambda I. So basically you can see that you are getting a minus lambda terms in all the diagonal elements. Now if you find the determinant of this matrix A minus lambda I, this will be called the characteristics polynomial. Now if you take equal to 0 matrix, equal to 0 determinant of this, then these equations will be called characteristics equation. So the polynomial is determinant of A minus lambda I and equation is that equal to 0. So these equations will be very much useful to find the eigenvalues and eigenvectors of a matrix. So simplest way, if you take the example here, so it is a 4 by 4 matrix, so order is 4. Now if we find the A minus lambda I, so what you will get? You will get the minus lambda terms in all the diagonals. So what you will get here? This one, right? So if you calculate the determinant, you know that as it is a upper triangular matrix. What is upper triangular matrix? So the below the diagonals all will be 0. This is called upper triangular matrix. See, in the case of upper triangular matrix, finding the determinant is very easy. You just multiply the diagonal elements. So here the diagonal elements are, this is first 5 minus lambda, then 3 minus lambda here, then again 5 minus lambda here, then 1 minus lambda here. So the multiplication of all this will give you the characteristics polynomial. If you make equal to 0 here, it will give you characteristics equation. Now you can think on important point here. If you multiply all these terms, definitely we will get the highest power of lambda is lambda power 4, right? Because you have total 4 numbers, so lambda multiply 1 2 3 4, so the highest power will be 4. So that you can write here that the characteristics equation of a matrix of order n, you will give you the equation will be always the degree also n. So here the matrix is 4 by 4. So the degree of the characteristics polynomial or the characteristics equation rather, you will get the 4. So this is one important point you have to remember. So this is the mathematical way to calculate the characteristics equation of a matrix. But in case of 2 by 2 matrix and 3 by 3 matrix, the process will be little bit easy. So if you see the process, so for the 2 by 2 matrix, you can find in the same way finding the determinant by putting minus lambda in the but this is also another process to calculate the characteristic equation for 2 by 2 and 3 by 3 matrix. For 2 by 2 matrix, the formula is lambda, as I discussed. If order is 2, then the highest power, that means the degree of the equation, will be 2. If order is 3 by 3 of the matrix, then this degree will be 3. So here lambda square minus s1 lambda, s1 is the sum of the diagonals of the matrix and s2 is determinant. So suppose if you have one matrix 1 2 3 4, I am saying example, let's say, so in that case the characteristics equation in that case will be lambda square minus the sum of the diagonal, that means 1 plus 4, which is 5 lambda, then plus s2 is the determinant, so 4 minus 6, so determinant is minus 2, so we can say minus 2 equal to 0. So this will be the characteristics equation of this matrix. Simple. Now for the case of 3 by 3 matrix, lambda q minus s1 lambda square plus s2 lambda minus s3. So you can see the sign will be the alternative, plus minus, and s1 is s2 is representing the sum of the diagonals, s1 sorry, and s3 is the determinant. Now another term you are getting s2. So in the case of 3 by 3, s2 is representing the sum of the minors of the diagonal elements. So if we take one again 3 by 3 matrix, 1 2 3 4 5 6 7 8 9. So here simply s1 is nothing but the sum of the diagonals, which is 1 plus 5 plus 9, which is 15. Now if you find s2, this is the important thing, sum of the minors of the diagonals. If you take the diagonals elements 1 5 and 9, then what are the minors? So the minor of 1 is, you have to remove the first row and first column, so remaining is 5 into 9 45 minus 48, so 3, plus the minor of the second diagonal element 5, that means you have to remove the second column and second row, so the remaining is 1373, so 9 minus 21, so 9 minus 21, which is minus 12. Then third diagonal element is 9, this one, so if you remove third row and third column, so 5 minus 8, which is minus 3, so minus 3 plus 3 will be cancelled, so the ultimate will be minus 12, s2. Similar way you can find the s3 determinant, is very easy, you know how to find the determinant, then you just put in that formula, lambda cube minus s1 lambda square plus s2 lambda minus s3. So s1 is simple, s3 also simple, s2 is the this concept, sum of the diagonal, sum of the minors of the diagonals elements, right? So this is another process to calculate the characteristics equation of 3 by 3 matrix. Whatever the easiest for you can use that. Either you can directly put minus lambda in the diagonal elements, then find the determinant of this, then make it equal to 0. This is another process, and the another process which I have discussed here, lambda cube minus s1 lambda square plus s2 lambda minus s3. Where s1 is the sum of the diagonals, which is called also trace. We can remember the sum of the diagonals also has a name, which is called trace of the matrix. Then s3 is the determinant and s2 is the sum of the minors of the diagonals. So this was the concept of characteristics equation. Now here in the all characteristics equation, one scalar value, one parameter value we can say we are using every time, which is called lambda. So this lambda is called eigenvalues of the matrix. So what is the definition of eigenvalues? If you have a matrix which is definitely square matrix of order n, then this lambda obtained from the characteristics equation determinant a minus lambda equal to 0, if you find the lambda value, then this will be called eigenvalues of the matrix A. That means simplest way you can write that if the characteristics equation you can find, and if you solve it, then you will get the roots of the characteristics equation, that will be the eigenvalues. So simply I have already told you, if you have matrix of 3 by 3 for example, then you will get the degree of the characteristics equation is 3, and you know that if the degree of characteristics equation 3, then the roots will be 3, number of roots, sorry, so the number of roots will be 3. So that means directly you can imply that if a matrix order is 3, then eigenvalues, number of eigenvalues will be 3. If the matrix order is 4, the number of eigenvalues will be 4. So rather you can say, if the order of the square matrix is n, n can be any number, positive integer. So that n will be the number of eigenvalues also. Now if you see the previous example, in the previous example this was the characteristics equation. If you remember, 5 minus lambda was twice 3 minus lambda 1 minus lambda. I have shown you the previous example of upper triangular matrix. Now this is the characteristics equation. I already told you that was the 4 by 4 matrix, so definitely you will get 4-degree characteristics equation. Now if you solve this, you should get 4 roots. So you can easily see that here 5 minus lambda is twice, so one is 5 minus lambda, another is again 5 minus lambda, 3 minus lambda, 1 minus lambda equal to 0. So all the 4 what is called factors are there. So if you solve it, you will definitely get lambda equal to 5 comma 5 comma 3 comma 3. So 4 roots you are getting. These 4 values are called eigenvalues of the previous matrix. You can remember one thing here, that the eigenvalues can be repeated also. Here you can see the 5 is the repeated values, right? So eigenvalues need not to be always distinct. That is another concept is there, which is called algebraic multiplicity, geometric multiplicity is there, but I am not going to discuss all these things here. So you can remember that the eigenvalues can be repeated also. It's not necessary that all eigenvalues should be different or distinct, right? So you can see these are the eigenvalues 5, 5, 3 and 1. Now there are some properties of eigenvalues exist. So let's discuss these properties. First of all, the property is, if a matrix is given, the sum of the eigenvalues is always the sum of the diagonals. That means the trace. Please remember, sum of the eigenvalues is nothing but trace. What is trace? Sum of the diagonal. Sum of the diagonals. This is one property. So if we find a matrix, one matrix is given to you, if you find the eigenvalues, to clarify or to verify that your eigenvalues is correct or not, you just make a sum and check that the sum is becomes equal to the trace or not. If not equal to, that means your eigenvalues are not correct. Okay. Next is that the product of the eigenvalues is the equal to determinant. This is also another process to verify. So the product of the eigenvalues is nothing but the determinant of the matrix, right? Now third is that if you have a square matrix and if you find the eigenvalues, now if you transpose the matrix, take the transpose, you know how to transpose, interchanging the rows and columns, then the eigenvalues will be the same. There will be no changes in the eigenvalues of a matrix after transposing also. Okay. Second thing, the eigenvalues of the triangular matrix, it can be upper triangular, it can be lower triangular. Also the diagonal matrix. So upper triangular, lower triangular and diagonal matrix. In these three cases, the eigenvalues will be the diagonal elements. Please remember, in the case of upper triangular, lower triangular and diagonal matrix, the eigenvalues will be the diagonal elements. No need to calculate. Without characteristics equation also, directly you can write using the property that as it is a triangular matrix, it can be upper triangular, lower triangular, then the eigenvalues will be the diagonal elements. So suppose if you have this kind of 3 by 3 matrix, I am taking example 1, 4, 5, 0, 3, 6, 0, 0, 9. So it is upper triangular matrix, you can easily see that. In that case, definitely the eigenvalues will be 1, 3 and 9, 100%. Okay. Next is that if a matrix is given and the eigenvalues of one of the eigenvalue of the matrix is lambda, then one of the eigenvalues of the inverse of the matrix will be 1 by lambda. Only case is that when the eigenvalues if not 0. If it is 0, then it should not be applicable because 1 by 0 will be indefinite, right? So if one of the eigenvalue of a matrix is lambda, which is non-zero, then if we find the inverse of the matrix, then one of the eigenvalues would be 1 by lambda, definitely. Okay. Third one is that a matrix is singular. So what is singular matrix? If the determinant is 0. and non-singular means determinant is non-zero. So as I already discussed, determinant is nothing but the product of the eigenvalues. So if one of the eigenvalues is 0, the product will be 0, that will be singular. So this is the necessary and sufficient condition, if and only condition. If a matrix is singular, then definitely one eigenvalue is 0. If also one eigenvalue is 0, that means matrix is definitely singular. Simple. This is the process to find the eigenvalues, the characteristics equation, and these are the properties of eigenvalues. Now concept is called eigenvector. So if you remember a minus lambda I, if we find the determinant, you will get 0. Then this lambda is called eigenvalue. Now if you take this a minus lambda matrix, and if we multiply a vector x with this, product of vector x with this, and you are getting a 0 matrix or 0 vector, then this x is called eigenvector, right? So if n is the n cross n matrix, A is the n cross n matrix, then x will be the vector of having n into 1. So that means x1, x2, xn. Now if you multiply this matrix with x, and if you equal to 0, then solve it. If you solve for x, and if you get the x, x1, x2 dot 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 x3, sorry, xn, this is called eigenvector. So what is the process? One eigenvalue. So for each eigenvalue, you will get each eigenvector different. So suppose you are getting, by solving this, you are getting 3 eigenvalues, lambda 1, lambda 2, and lambda 3. Then one eigenvector you can write a minus lambda 1I. Suppose capital X1 I am writing. So if you solve it, you will get capital X1 for lambda 1. Similar way, another eigenvector is lambda 2. Here you will write capital X2. So if we find the capital X2, it will be the eigenvector for corresponding to lambda 2. So this way you have to find the eigenvectors of a matrix. So if you have different eigenvalues, you have to calculate the different calculation. Then you have to calculate the eigenvector for corresponding eigenvalue. Okay, so this is the definition of eigenvector. So if you remember, I have already discussed in the beginning that eigenvector is nothing but a scaling of this matrix, right? So multiplying this matrix with x, and it is giving you 0. So now we'll do the mathematical calculation. So if for the simplest understanding, we'll take, or you will consider a 2 by 2 matrix by starting. So if you take this example, 2 by 2 matrix. So first of all, we have to calculate the eigenvalues, as I discussed. So to calculate the eigenvalues, we have to find the characteristics equation. So I have discussed the characteristics equation formula, lambda I minus a, then take the determinant. So lambda I minus a, or a minus lambda I also you can say. There will be no changes in the eigenvalues. So if you take lambda I minus a or a minus lambda, both are same. So if you lambda minus a means in the diagonal you have to put minus lambda, or lambda minus this. So this and this you are getting. Then determinant you have to calculate. Otherwise for 2 by 2 matrix I have already discussed, lambda square minus s1 lambda. S1 is the sum of the diagonal trace. So minus 5 plus 2 minus 3, so minus plus 3 lambda, plus s3. S3 means determinant, so minus 10 plus 12, which is 2. So definitely you will get this one. Easy. So if you solve it, after solving we will get 2 eigenvalues, because it is 2-degree equation and at least a 2 by 2 matrix. So if we solve it, we will get one value is minus 1, one value is minus 2. Simple. So this is one eigenvalue, this is another eigenvalue. So the eigenvalues we have calculated. Now you have to calculate eigenvector for each eigenvalue different. So I have discussed for lambda 1 equal to minus 1. I have discussed already a minus lambda or a minus a lambda minus a, both are the same case. Now a minus lambda or minus, so if you calculate this one, so minus 3 you will get, because lambda 1 value is minus 1, so minus 1 minus 2 minus 3, 12, like that. So this is this, and I have taken the vector x1 x2 here equal to 0 vector 0 0. Now you just solve it. So if you solve it, by using system equation formula, you know, if we convert this to the row econal form, I have already discussed in my previous lectures how to convert a row econal form. So if you find the row econal form, so only one equations you are getting, x1 minus 4x2 equal to 0. So if we solve it, we will get the values is 40 and t. So if you take common t, we will get 4 and 1. How to get it, I will discuss here. If you see, so if you see 1 minus 4, so you will get x1 minus 4x2 equal to 0. Only one equation and two variables you are getting. So one of the variables you should take as a t. So if you take x2 as a t, so definitely x1 will be 40. So 40 comma t will be the eigenvectors. T if we common, so 4 1. If t is not 0, because eigenvectors should not be 0 vector. Please remember, this is the very important note. Eigenvector cannot be a 0 vector. Please remember. So t should not be 0 here, otherwise it will be 0 0. So t can be any scalar other than 0. So that means if we change the value of t, you will get different eigenvector, but the form will be 40t. If t is 1, then the eigenvector will be 4 1. If t is 2, the eigenvector will be 8 2. If t is minus 1, then minus 4 minus 1. So this is the form, or this is the eigenvector of the matrix with respect to, or you can say corresponding to, lambda 1 equal to minus 1. Now similar process if we follow here for minus 2. So minus 2 minus 2 minus 4 minus 12 as it is. 1 is, sorry, it will be, sorry, here the question was given minus 1. Okay, this is minus 1. So minus 1 same. Then minus 3 minus minus plus, sorry, minus 2 minus plus 5 is 3. So again you have to convert to the row econal form. So after converting row econal form, you are getting this. So after this, what you are getting again, x1 minus 3 x1 x2. So you are getting x1 minus 3 x2 equal to 0. So ultimately, if x2 is t, x1 is 3t. So the eigenvector will be 3t. T can be common, so 3 1. This will be the eigenvector. Suppose v2, and this is suppose v1. So v2 is the eigenvector, which is 3 1 or 6 2, like that. But depending on the t, you can take any t. So this is the eigenvector for the of the matrix corresponding to the eigenvalue lambda 2, which is minus 2. So you can just extend this same process, apply the same process for 3 by 3 matrix also. Okay, so you will get the eigenvectors. So this was the concept for eigenvalues and eigenvectors. Again, I am repeating. For eigenvalues, first of all, you have to calculate the characteristics equation. How to find the characteristics equation? Just put minus lambda in the diagonal elements of the matrix, then find the determinant of this, then make equal to 0. So you will get the n degree equation if the matrix is nth order. If matrix is 2 by 2, you will get 2 degree equation of characteristic equation. If matrix is 3 by 3, you will get 3 degree equation. If it is 4, then 4 degree. Then if you solve or finding the roots of the characteristic equation, you will get the eigenvalues. Okay. Now take one by one eigenvalues and calculate a minus this lambda 1 or lambda 2, whatever the eigenvalues you are taking, a minus lambda 1 x equal to 0 vector. Calculate the x by reducing to the row econal form. This x will be called the eigenvector corresponding to this eigenvalue lambda 1. Similar process for lambda 2. If it has 3 degree equation or 3 eigenvalues, then for lambda 3 also same. So this was the concept eigenvalues and eigenvectors. These are the some examples. You can try it. It can be homework. So I'm just giving a flow chart. This is the flow chart you can follow. So calculate characteristic equation, solve it for lambda, then solve it for x for each eigenvalue. Another example, application of characteristics, eigenvalues and eigenvector is called Cayley-Hamilton theorem. So I will discuss this also. So what is Cayley-Hamilton theorem states? The statement of Cayley-Hamilton theorem is saying that every square matrix satisfies its own characteristics equation. It's very simple. If you take a square matrix, if you calculate the characteristics equation, it would be in terms of lambda. Then if you substitute lambda as a matrix, then definitely it will satisfy. This is the characteristic, sorry, this is the Cayley-Hamilton theorem is saying. Now, what is the application of this? Is very much applicable to calculate the integral power of matrix A. If your matrix A is given, sometimes to do the manual calculation to calculate a cube or a power 4 or a power 5 is difficult. It will help you to calculate this kind of integral of power of the A. Second is that to calculate the inverse of a matrix, you know there are numerous uh, method to calculate the inverse of a matrix, Gauss-Jordan method, then using the adjoint A by det A. But one of the method is also Cayley-Hamilton theorem. If you know that, if you calculate the characteristics equation, then if you satisfy the A of this characteristics equation, then you can easily calculate the inverse of the matrix. So we'll discuss one by one this. So what is, so our their statement, Cayley-Hamilton theorem statement is correct or not, so we should verify once. Okay, so I'll give an example to verify that the characteristics equation of a square matrix is satisfying by the matrix itself. So if you take, we'll take a simple example of 2 by 2 matrix A. Suppose I am taking 1 1 minus 2 4. Simple. Now what is the very first thing we have to do? We have to calculate the characteristics equation of this. So what will be the characteristics equation of this? Det of A minus lambda I equal to 0. This is another process. Otherwise we can calculate lambda square minus s1 lambda plus s2 equal to 0. S lambda square, s1 is the summation of this diagonals, so trace, so 5 lambda, then s2 is the determinant, so 4 minus minus plus 2 is 6. So we are getting the characteristics equation is lambda square minus 5 lambda plus 6 equal to 0. Now what is Cayley-Hamilton theorem is saying? So Cayley-Hamilton is saying that CH theorem, if we apply, so if we substitute lambda with A, so a square minus 5a plus 6, it should be equal to 0. Now please remember one thing here, we are replacing lambda with A. Lambda was a scalar, now we are replacing with matrix. A is the matrix, so a square is fine, minus 5 is fine, so a square will be again a matrix of 2 by 2, 5 also will be a matrix of 2 by 2, but 6 is the scalar, so you cannot add. So all, please put a I, identity matrix, whenever you are getting the scalar. So you should put its I here, identity. Definitely it will be 2 by 2 identity because the matrix is 2 by 2, right? So this should be satisfied, this should be equal to 0 matrix. This is the statement of the Cayley-Hamilton theorem. Simple. So if we calculate a square, if we calculate 5a, if we calculate 6i, then a square minus 5a plus 6i, if we do the calculation, you will easily see that it should be 0 matrix because it is already proven. So I am not going to prove here. You can easily see that it will be verified. Calculate all these things, it should be easily verified. Now I am going to discuss that how this matrix is, this statement is useful to find the inverse. So if you write this, a square minus 5a plus 6i equal to 0, and if you take only the constant 6i this side and take others this side, minus a square minus plus 5a, then if we divide 6 this side, so 1 by 6 minus a square plus 5a, then multiply a inverse both side. So I into A inverse is definitely, you know, I is identity matrix, multiply any matrix, you will get the same matrix. So A inverse you will get 1 by 6, then minus a square, so a square into A inverse you will get is only A, plus 5 into A inverse, so you know that A into A inverse will give you the identity, so 5i. Now you know the A value, you know the 5 value, just substitute here. So I am calculating here, it is so what you will get, A inverse equal to 1 by 6 minus a, so minus a means minus 1 2 minus 4 plus 5i means 5005. Now you just calculate it, 1 by 6, it will be 4 minus 1 2 1, so this will be the inverse. So you can see, you can extend this concept to 3 by 3 matrix, 4 by 4 matrix, same process you have to apply. So this is one of the application of eigenvalue eigenvectors, that you can calculate the characteristics equation. So just sorry, it's not eigenvalue eigenvector actually, it's just characteristics equation is required. So you can say it is an application of characteristics equation finding. Then you can easily calculate the inverse. Even also you can calculate the power of the matrix. Like for example, same example if we take. So what is the equation is saying? Lambda square, so sorry, a square minus 5a. So if you write it here again, a square minus 5a plus 6i equal to 0. So if you calculate a square, what you will get? 5a minus 6i. Please remember. Now multiply a cube both side. A both sides. So you will get a here, a cube here, 5a square minus 6i into m is a. Then again a square value you have already calculated, substitute here. So 5 into 5, 25a. 5 into 6 minus 30i minus 6a. So you can calculate, it will be 19a minus 30i. So a cube also you can easily calculate. You know a, you know I, just substitute. So if we know the characteristics equation, then use the Cayley-Hamilton theorem, then you can calculate the power of a cube. Similar process, you can just multiply a both side, you will get a power 4, and also you can calculate inverse. So that's all for this lecture. In this lecture, we have discussed about characteristics equation to finding eigenvalues, eigenvectors, and the application part, Cayley-Hamilton theorem. So, okay. So, goodbye. We'll meet again in the next lecture. Thank you for watching me.